Alright, let's do another problem. Today we're going to be working on same tree. This is number 29 of my grind 75 journey. Let's take a look. Given the roots of two binary trees, P and Q, write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical and all the nodes have the same value. Okay. Okay. So there are a couple ways that we could do this. We could do this in an iterative manner. So we could do like run a specific check to see if the nodes are the same. So I'm talking about like a traversal to be exact, like a pre-order, in-order, post-order sort of thing, and check each node. Or we could do a recursive solution. And what I'm imagining is, and this is a complete theory at this moment, but a tree is the same as another tree if and only if the left and right subtrees are identical. I.e., if we check the current node, the left subtree, and the right subtree, and they are all the same, then we have the same tree. So I'm leaning towards this solution since it's just the most, I guess, intuitive for me. So what I imagine is that, first of all, if P question mark dot wrong val is equal to Q dot val, how should I? So basically, I want to check to make sure that the nodes are the same. If P is not null and Q is not null, else, that means one of them is null, so we return false. If P is actually no, because they could be both null. Actually, I think a when block might be nice for this. If P is null and Q is null, if P is not null and Q is not null, else I think this is just returned false. If they're both null, return true, because in this case we're at the end of the line basically. There's nothing else to check. If P is null and Q is null, then there is no left, there is no right for either of them. If both of them are not null, then return P dot is same tree, P left, Q left, and is same tree, P right, q right. So basically the idea is that if both of them are not, let's see, p dot val is equal to q dot val. So if they're both null, we know that they are technically the same because they are both null. If they are both not null, then we need to check their values and we need to check their left and right. If one of them is null and the other is non-null, then we know for sure that it is not correct and we can just return from there. We don't even need to check the rest of the tree. So let's give this a shot and let's see if there's anything that we need to change. So that worked out fine, the first example. Let's run the rest of them and let's see. Okay, that seemed to work. Let's give this a submission. That is slow. Okay. That is incredibly slow. 9.69% fast. Okay, then there has to be some way of checking in a faster manner. Is there some other way that we can optimize this further? That is a good question. Thinking about this in a recursive manner, how fast is this? Well, if we check the node and we check, say that all of the nodes, it's like basically a perfect tree for both of them. We start at the root, both of them, then we check the left, then we check the right, then we check the left, 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 right, right, left, right, right, and so on and so forth. At the worst, we would need to I guess the main thing is that at the leaf level, if there are a lot of leaves, then we are calling this is same tree on a lot of nulls. So we can say that val same value. Oop, did not mean to do that. Q dot val. Val left value is equal to if p dot left and q dot left, not null, not null, is same tree else true. Actually, I'll put this as right same and left same. And basically just checking that if they are both non-null, this is difficult because they technically need to run through the same exact thing. Otherwise, there's no... Because if one of them is null, then we want this to return false. If both of them are null, so we'll do that instead. We'll do an or rather than an and. So that way, the only case where we skip is at the leaf level, which is the most expensive level. And this is at the point where we would say, that if both of them are null, we're at the leaf level, both of them are null, so this isn't, so this will not be true, so then we just return that. So that might cut down on runtime slightly, but we'll have to see. Okay, that's a little bit faster because we just eliminated a lot of checks at the leaf level. I think at this point, at the worst, we would be checking all the nodes. I think that if we were to take this in an iterative manner, we could skip out on a lot of it. Because we could, once we find anything that doesn't match, then we can instantly jump out of our checking and we can say everything is wrong, right? We don't have to check the remaining parts. Whereas in this one, we're sort of forced to carry it out to the end. However, even in that iterative manner, in our worst case scenario, if we have a big tree and they are the same, then we would still have to check every single node. So I think ultimately this is fine as it is. It might be slower than an iterative solution on certain cases where we don't have the same tree, but I think on an asymptotic level, this is actually perfectly fine, in my opinion. Who knows? Maybe, and I'll probably double check the solution later on to make sure, but I think this is perfectly fine. And this would be the type of solution that I would submit in an interview, and I think that even though a recursive solution may not be the fastest, I think that it's more legible and I think the intuition makes a lot more sense. But that's going to be it for today's video. So 48.98% speed for runtime and 35.46% memory usage. That'll be it for number 100, same tree, and I'll see you all in the next problem.